This video is going to go over the kinetic energy of rolling objects. So let's say that we have a disk that is rolling across a surface. We can assume that the point of contact at a given instant is at rest. This makes sense because the disk grips onto the surface and doesn't slide as it rolls across the surface. So we will call this point of axis, this point the axis of rotation for the rolling disk. All of the other points on the disk are rotating with respect to this axis of rotation. And these points are going to have different velocities but the same angular speeds. Keep in mind that the angular speed is defined as a point's velocity divided by the distance away from the axis of rotation. So the further the point is from the axis of rotation, the faster velocity it will have, so everything balances out. Now let's approach this problem a little differently. We have a disk here that is rolling, and the center of mass is traveling at a velocity of v, which means that the outside of the disk is traveling at a velocity of 2v. And this is because the top of the ball is a distance of 1 diameter or 2 radii away from the contact point, which is our axis of rotation. And the point in the center, or the center of mass, is only 1 radii away from the contact point, which is also our axis of rotation. Now we can say that this rolling movement is a combination of two other kinds of movement, which is translational movement, which we can assume is just the disk traveling towards the left, all at the same velocity. This would be the same kind of situation as if we were just going to drag this disk across the ground. And the second kind of rotation is purely rotational motion, where the linear velocity at the top and the bottom of the disk are pointing in opposite directions. So if you take a look at the two different diagrams below, you will see that the velocities at the contact point at the bottom are pointing in the opposite direction, so they will cancel. And the velocities at the top are pointing in the same direction, so they will add. So when we combine our two diagrams on the bottom, we get the same diagram on the top. The next step is to derive the equation for kinetic energy for a rolling object. We know that the kinetic energy of a rotating object is equal to 1/2 times the moment of inertia for an object multiplied by the angular velocity squared. So if we assume that our rotating disk looks like it did on the first slide, we would say that the contact point was stationary and all the other points rotated around it. So our kinetic energy equation would look like this. Our next equation comes from the parallel axis theorem, which you can search for on your own if you're curious about. But it essentially says that the moment of inertia is equal to the moment of inertia about the center of mass, plus the object's mass times the distance away the new axis of rotation is from the center of mass squared. So we can multiply everything out, and we are left with this equation. And if we think about rolling as a combination of translational and rotational motion, we can see that the translational motion would have the kinetic energy of 1/2 mv squared, and the rotational kinetic energy of 1/2 times the moment of inertia times the angular velocity squared. So let's say that you were asked to compare the kinetic energy of a rolling solid sphere, disk, and hoop that all have the same mass, center of mass, and velocity. So we know our generic equations begin with 1/2 mv squared plus 1/2 I omega squared. And the only thing that's different about these objects are their moment of inertias. And also we can substitute in v over r for omega because of this relationship we have, and it simplifies and takes out another variable. And our moments of inertia for the sphere, disk, and hoop are defined on the previous video, so we can simply just fill in these values. So now we have equations for the kinetic energies of these different rolling objects. Let's do one more example. A solid sphere with this moment of inertia has end of radius r rolls down an incline of height h, starting from rest. Determine the speed of the center of mass when the sphere reaches the bottom. So we know that mechanical energy is going to be conserved here. And the sphere begins with only gravitational potential energy, so mgh. And after it is only going to have rolling kinetic energy, which we said was equal to 1/2 mv squared plus 1/2 times the sphere's moment of inertia times the angular velocity squared. So we can plug in our moment of inertia and simplify our version of omega, and conveniently some of the variables cancel, and we're left with the velocity of the square root of 10/7 times gravity times the height.